Review paper on the unstarting of the supersonic air intake. Abstract: ramjet engines propel the vehicle at supersonic speeds, i.e., m1. Compression eventuates inside the ramjet engine at subsonic speeds, i.e., m1. The freestream supersonic flow has to be the commute to subsonic speed through air intake, which compresses the flow. Its supersonic intake efficiency determines the performance of the ramjet engine. To get efficient performance, the required quantity of air should go inside the air intake. Based on compression, 3 types of intakes are in use: external, internal, and mixed compression intakes. While the internal compression problem of unstart has been there, which is responsible for reducing the inefficient performance of the ramjet engine, the present paper reviews different techniques to solve the problem of unstart using different techniques of supersonic air intakes. Keyword: supersonic, bleed, vortex generator, starting and unstarting. Introduction: an air-breathing vehicle's main function is to capture the required airflow for an efficient combustion process. In-vehicle intakes that operate at supersonic speeds are used. Compression in the intake should be done with minimum losses to increase the engine's overall performance. 1. The unstart of intake or the buzz phenomenon, which is responsible for losses in the mass flow of air that enters inside the intake, and external surface drag, also increases intake and other losses that affect intake too. The intake should have a maximum pressure recovery with minimum losses. In combustion, some heat losses occur, which creates some amount of back pressure from the exit of the intake, which destroys the shock wave pattern and causes the phenomenon that leads to the unstart of the intake. 3. The intake design should be like this so that it can endure losses. The engine's overall performance and the vehicles depend on how much quality and quantity of air are captured by an air intake. Losses from that are responsible for a decrease in an engine's thrust force. 4. Intake should be in a supercritical or subcritical state to gain the maximum efficient performance and stay away from the subcritical state, which creates the buzz. Like external losses of intake, it has inside losses like losses in shock wave boundary layer interaction, the effect of drags, flow separations, the absence of proper mixing of boundary layers, etc. These are the internal factors that lead to the unstart of intake. 5,2. There are several techniques which prevent this unstart, which have already been done. Starting and unstarting of the intake. A. Starting of the intake. The performance of a mixed compression air intake system is measured by its ability to deliver the required mass flow to the engine while minimizing total pressure loss and flow distortion. 2. 6. One of the major problems associated with mixed compression intakes is the unstart process. This phenomenon will influence the flow field's mass flow rate and characteristics inside the intake and could also affect the stability of the engine. Generally, unstart of the intake is observed through the expulsion of the shock system and massive spillage, leading to degraded pressure recovery and large flow distortion at the exit. The intake's unstart could occur for several reasons, e.g., overcontraction, the variation of flight conditions, perturbations in combustor operation, back pressure, angle of attack, etc. To a combined effect of these factors, the presence of flow-induced separation in the internal duct could also lead to unstart of the intake, generally termed soft unstart. 2. 7. During the operating condition of an intake, flow can be achieved in 2 ways. 1. At designed Mach number conditions, the intake will capture a significant amount of mass flow, which creates equivalent shock waves, which results in proper compression happening due to extension in total pressure and reduction in Mach number. This is called the start of an intake. 8,10. At the time of operating conditions, shocks are generated as intake is designed, as shown in Figure 1. Inside the intake, normal shocks are stronger than those normal shocks which are produced on transonic wings or in turbine machinery with upstream Mach. B. Unstarting of an inlet. 3 types of disturbances are responsible for the unstart of an intake. 1 is a reduction in incoming flow Mach number, the second is due to a higher value of back pressure during the operating condition, and the third is due to blockage effect 2 due to non-uniformity in the amount of mass flow at different sections inside the intake. The flow will rapidly move upstream at the start of intake. Unstart is the choking of flow due to upstream mass flow greater than downstream mass flow. The buzz is created by the decrease in stagnation pressure within supersonic intake. As a result of buzz, shock waves are unstable and oscillate within an intake or reach the converging part. During an unstart, when bow shocks are introduced, the reduction in mass flow and internal structure integrity has been reduced. 1. It also increases the external drag. Figure 2 depicts the unstarting of an intake. 5. The problem of an unstarted operation happens in the operation of internal compression. The ability of a supersonic mixed compression intake to deliver the required amount of mass flow to the engine while minimizing total pressure losses and flow distortion, This affects the intake 2,4,9. Processes to control unstart of an intake. Due to the higher value of back pressure, unstart has been happening 11 due to the unstart of an intake shock oscillation, pressure fluctuation, etc. have been introduced. The Ferry condition is defined by moving shock across the cowl lip from outside to inside. There are various methods that have been used to control the unstart of an intake. 1. Variable geometry supersonic intake. 2. Bleed slots in supersonic intake. 3. Supersonic intake with cowl lip deflection. 4. Microvortex generator in supersonic intake. Results. Controlling the mass flow in the intake is the primary solution to the intake. Through variable geometry, mass flow is controlled, and Neal and Lamb did the experimental studies. There have been improvements in the results 12,13. Another solution to controlling the unstart of the intake is to provide the intake's bypass doors, which are used to release pressure during necessary conditions. As shown in Figure 3, the figure for controlling the mass flow bypass doors is working 14. Providing bleed slots inside the intake is an excellent way to prevent losses. Location, design, and proper sizing are necessary to achieve the engine's efficient performance. 15. Providing the bleed slots at those locations where the shock is going to be attached as per design, which converts the weak shock to a strong shock due to the reduction in the shock wave boundary layer. 16. Bleeds are suppressed by the shock wave's boundary layer. Possible locations of bleeds are on ramps, cowl lips, and at the sidewall. Bleed can be provided in holes, slots, and scoops, as shown in Figure 4. 5 boundary layer bleeds are used to avoid boundary layer separations and to minimize the total pressure losses. Bleeds are used to keep the normal shock within an intake stable. 17. Experimental investigation into mixed compression intake with bleed and cowl bending done by 7 results show flow improvements near the throat sides, which enhance the performance of an intake and prevent the starting problems of an intake. But S. Das and J.K. Prasad did an experimental and computational investigation on cowl bending with bleed 7, providing the bleed mass flow ratio decreased, but the improvement was noted in the performance of an intake as shown in Figure 5.5. At starting conditions, shocks are attached to the cowl tip. The reflected shock attaches to the ramp surface boundary layer, which creates some unsteady conditions inflow and a reduction in performance inside the intake. 5,2. Experimental and computational study on supersonic mixed compression intake with different cowl deflection angles. A computational study has been conducted with freestream Mach number 2.2 with different cowl angles of 1 degree, 2 degrees, 3 degrees, 4 degrees, and 5 degrees, and also with a back pressure effect. 18. An increase in cowl angle deflection performance was noted. In compared to all the data, 2 degrees cowl deflection with 2.8% bleed shows maximum efficient performance compared to others presented in intakes due to the effect of back pressure extension on flow separation inside the intake has been seen and the flow gets distorted at the exit. Figure 6 depicts the position of the normal/terminal shock going to the cowl side as the cowl deflection increases. Figures 7 and 8 show the pressure distribution on the cowl and ramp surface, respectively. 18. Microvortex generators in supersonic intake. Microvortex generators reduce the momentum of flow from high to low near the wall with minimal parasite drag. 4. Microvortex generators have a thickness less than the boundary layers of flow. They are responsible for reducing the viscous drag because of the small wetted area. The microvortex generator's principle controls the shock wave boundary layer interaction through controlling the boundary layer, and they prevent the induced separations. 5. Counter-rotating vane-type vortex generators are more efficient for eliminating shock-induced separations than the ramp-type microvortex generator. Vortex generators in various shapes. Shown in Figure 9. From the use of microvortex generators, Bobinski did the experimental analysis at Mach 2.5 and in results improvements in pressure recovery and distortion noted. 20. Conclusion. The mentioned techniques are responsible for improvements in the internal and external losses of a supersonic air intake. To prevent the starting and unstarting problems of a supersonic intake, the present study includes the literature review on bleeds, deflection of cowl lip, microvortex generators, and variable geometry, which shows the improvements in shock wave boundary layers as well as reducing the separation of flow inside the intake. By using those several techniques, an increase in pressure recovery is also noted from the results.